Hello and welcome to the first lecture of ECG. Here we are going to discuss the first topic, that is the basics of ECG. Okay, we are going to start from the very simple depolarization and repolarization waves. Here actually we're gonna study the depolarization part. Okay, and here we are going to study the repolarization part. Then after that, using all that knowledge to put it on a normal heart. See, this is the normal heart, very ugly human being, but it's okay. Sorry for that, my drawing is not so good. Then after that we're gonna apply it for on the normal heart, which is going to make the normal physiological waveform of the ECG P, Q, R, PQR, S, and T. Okay, this is the normal physiological waveform of the ECG. Now let's get started with a very simple concept of resting membrane potential, action potential, which I'm going to discuss shortly. This is the normal cell of the human being. See, all the cells in the human being are negative inside, minus 90 millivolt inside the cardiac cell and minus 70 millivolt inside the nerve cell. And see, all the human cells are negative inside. This is known as the resting membrane potential, and this resting membrane potential is actually the potential when the cell is resting. Now if you are going to make it excited, then this cell is going to lose its negativity and it is going to convert to this form, positive form. Now this cell is known as depolarized cell, or you can say excited cell. Okay, now after excitation it should go to its normal state so that it can get excited again. Okay, so now from the excited state it will go to the non-excited state again, which was like this, right? And this is known as repolarization state of the cell. So this depolarization and repolarization is occurring, and it is going to make the cell positive and negative. Okay, now we are going to put all these cells and on a sheet, see, and when we collect lots of cell together, that is known as tissue, right? See, this tissue is consist of lots of cells, and this cell is negative. These cells are all negative inside. See, it means that these cells are not excited, and these cells are connected to each other. Now we are going to give a stimulus from this side, and it is going to get excited. Okay, so let's see, when we give the stimulus to these cells, let's consider these cell get excited, is going to convert to positive state. Then these cells are connected, as I said, it is going to give its charges to this cell, and the action potential is going to produce along like this, and this cell will become positive. After that this cell will become positive, and the action potential is going like this. See, now what is this? This is getting positive, right? Now if I draw it in an arrow form, this is actually the wave of depolarization going like this, right? Wave of depolarization, we can put a charge here, positive, right? Depolarization, positive, right? And then after that repolarization will be occurring, right? So if these cells are getting repolarized, it means that again they are losing this positive charge, and it will become negative, 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 like this, right? Okay, so the repolarization will also go like this. First of all, depolarization, right, which will make this arrow, and above its head there will be a positive charge. If we now draw a wave of repolarization, it will be like this, understand? And we will put the negative charge over its head. So this is a wave of depolarization, this is a wave of repolarization. Okay, now let's connect this galvanometer with this tissue, which is consist of lots of cells. It's drawn on this page. Okay, so this is the galvanometer, and it is connected to this tissue with the help of positive electrode, which is coming from this galvanometer, and negative electrode, which is coming from this galvanometer. Okay, and see, this should be normally negative, right? Now let's do a very simple math that everyone should know from their primary, that positive into positive gives you positive, right? And negative into negative gives you positive. Then negative into positive or positive into negative are going to give you negative, right? Everybody knows it. Same principle are going to be applied over here. We are going to stimulate this tissue from here, and when we stimulate this tissue, action potential is going to be produces this tissue along the way, like this is going to be depolarized, and when it get depolarized, depolarization wave is going to produce like this. See, we can draw it in an arrow form like this. I'm sorry for my drawing, but accept it anyhow. Okay, this is the arrow, very ugly. And on this arrow's head, there will be positive charge, right? Because it's a wave of depolarization. Now let's see this. This wave of depolarization is going toward the positive electrode of this galvanometer. So the deflection should be towards positive side. Positive deflection will be occurring. Okay, I'm producing this angle, that's why the bulb point is not working properly. Okay, this is the wave of depolarization. Okay, same is the case when this depolarization wave is finished. After that, repolarization is going to be occurred along the way, and repolarization wave will be like this. See, and this repolarization wave should be drawn like this. This is the arrow, and this is the wave of repolarization. So we're gonna put negative charge over its head. Now let's see that wave of repolarization, that is negative, is going toward this positive electrode, and here we have studied that negative and positive gives you the negative result. So this deflection is going to be negative. The deflection of this needle will come toward the negative side. Same is the case over here. Now we are going to stimulate this tissue from this side, right? Now we stimulate if this tissue from this side, depolarization is going to be occur like this, right? So it will get depolarized, it will get depolarized, depolarized, depolarized like this, right? If we draw it in an arrow form again, the arrow will be like this, right? And this is a wave of depolarization, so we're gonna put a positive charge over its head. See, now when we are going to draw the wave of depolarization, positive wave is going toward the negative electrode over here. So negative into positive equals to negative. The deflection of this needle here is going to be to the negative side. See, this will be the deflection. Now see, wave of repolarization will be followed by, okay, see, wave of repolarization. So repolarization will be occurring like this, see. Now the arrow of repolarization, see, this is a negative wave, is going toward the negative electrode. See, wave of repolarization is going toward the negative electrode of the galvanometer. See, and negative into negative is equal to positive. So here the deflection of the needle will be towards the positive side. This will be the deflection. So this was actually the deflection of the needles because of way of repolarization and depolarization. I would suggest that if you haven't understand, you can rewind the video 2 or 3 times. You will understand it very clearly, and I hope that you will understand it even by watching it on first time. But still, if you don't, you just rewind it 2 or 3 times. Now we can rewind the depolarization and repolarization quickly on this chart. Okay, so this is the galvanometer, which is connected with the help of positive electrode and negative electrode to this tissue. We're going to produce the wave of depolarization by stimulating the tissue from this side. So wave of depolarization, that is the positive wave, is going like this, right? Positive electrode here, this arrow is showing it. So positive is going toward the positive electrode of the galvanometer. It is going to cause the positive deflection of the needle toward the positive side of the galvanometer. Okay, now repolarization of this will be starting over here. This is the wave of repolarization. See, this is negative wave. This is negative wave, see, and negative is going toward the positive. So negative into positive equals to negative. The deflection will be toward the negative side of the galvanometer. Okay, here now we are going to stimulate the tissue from this side. There we stimulate it from that side, right? Now we're gonna stimulate it from this side. This will be depolarization, and here we will study its repolarization. So depolarization wave is going from positive electrode. See, this is positive and this is negative. Wave of depolarization wave is positive wave, right? Positive is going toward the negative. Now even this is wave of depolarization, positive wave is going toward the negative. Positive into negative equals to negative. So the deflection of the needle will be to the negative side of the galvanometer. Now when its repolarization occurs, repolarization wave will be start from here, and repolarization wave, as we know, that it's a negative wave. This is repolarized, and it is going to be repolarized, getting negative, but it's still positive, right? So this is the wave of repolarization. On its head there will be negative charge, and negative, when goes toward a negative, it is going to cause, yeah, you're right, positive deflection. So there will be positive reflection of the needle on the galvanometer. Okay, so these are actually the vectors. Now we are going to study the normal electric physiology of the heart. Okay, to understand it, we need to go to this diagram over here. See, so this is actually the SA node. From the SA node, an automatic current action potential is going to produce. It has the automaticity, everybody knows it, right? It is going to produce the current, and it is going to depolarize the cardiomyocytes of the atria first. All the cells of the atria are going to get depolarized. Okay, after that, this current is coming to the AV node. Okay, in the AV node, it will delay for some time in order to finish the contraction of these atria and ventricles, and then after some time it will come to downward to the ventricles. In between the two ventricles there is interventricular septum, and through this septum it will come down through the bundle of His. This bundle of His is going to divide to two branches. This is right bundle branch, and this is left bundle branch. Okay, the action potential, or you can say the depolarization wave, is going to spread like this, and right and left bundle branch are then divided further to Purkinje fibers. Okay, and these Purkinje fibers are going to give the electric current to the muscle of the heart in order to contract. Okay, so this is actually the normal physiology of the electrical activity of the heart. SA node to the atrium, to the atria, AV node, bundle of His, right bundle branch and left bundle branch, and then after that Purkinje fibers. Okay, we are going to see the vectors, that how these vectors, that we just drawn before that, how does it produces on this heart. Okay, so we will start it from the atria. From the SA node, it will produce like this, right? The current is coming to the atria. When you take the combined vector of all these current coming like this, it gives a vector like this, and you know that it is a wave of depolarization, right? So the wave of depolarization, over the head there will be positive charge. Okay, then it will come to the SA node, AV node. Okay, after that it is going to come toward the septum. When it is going to depolarize the septum, it is not depolarizing the septum in this way. It is going to depolarize the septum from bottom to top. Okay, and it is also a way of depolarization. Here also you will get the positive charge. After that it will come to the bundle branches, and then after that it is going to depolarize the whole ventricle like this. These are all the vectors, small vectors, which shows all the cardiomyocytes of the ventricles. But if you get a combined vector from all these vectors, the direction of the vector will be like this. See, and this is also a way of depolarization, so you will get a positive charge over here as well. Then this current will go like this, and these are actually the last part of the ventricle which are going to get depolarized, which is shown over here. So these are the last part of the ventricle which are going to get depolarized. You'll also get the positive arrow on this vector, okay, and this as well. See, after that the wave of repolarization is going to start. This is repolarization wave, so sorry, repolarization wave is always negative, and the repolarization of the ventricle is from down to up. Okay, depolarization like this of the ventricle, and repolarization is always like this. Okay, so remember this thing, because we're gonna apply it on the normal physiological form of the ECG. Now we are going to put all these vectors on one diagram of the heart, and we're gonna put this heart in a very ugly human being, sorry for that. This is the diagram. We have put it over here, the heart SA node. This is the way of depolarization at atria. Okay, it should be positive here. Okay, then it will come to the AV node, then interventricular septal depolarization, which is from down to up, then ventricular depolarization. This is the main ventricle, and these are the bases of the ventricle. So main ventricular depolarization is like this, the vector is like this, and when the current to the bundle branch goes to the base of the heart, this part is going to be depolarized, and depolarization of this part is also like this. Okay, so this is also depolarization vector, which will be positive as well. So atria downward, interventricular septum upward, ventricular major ventricular portion is downward, the base of the ventricle upward. Okay, now we have put this heart in this human being. See, and now what we are going to do is connecting a galvanometer to this heart to see the electrical activity of this heart. So this is the negative electrode, we have connected it to the right hand. This is the positive electrode, we have connected it to the left foot, and this positive electrode is connected to this side, and negative electrode is connected to this side of the galvanometer. Okay, now look at this needle of the galvanometer. For understanding purposes, I have put it out of proportion, right? This is the positive side. When we get the positive deflection, it will be like this. This is the negative side of the galvanometer. When we get the negative deflection, it will be like this. Or we can put it in other words, when there is positive deflection, it means upward deflection. When there is negative deflection, it means that it is downward deflection. Now what we do is that put ink or color on this head. Okay, We take a paper. See, this is the paper. Okay, now let's assume there is nothing on this paper. See, let's consider this paper is blank. I will get a blank paper. Okay, and instead of this needle I will put my ballpoint over here. Okay, and we know that on the tip of this there is ink. So when this paper is constantly moving under this pen, see what will happen when there is positive and negative deflection. See, this paper is moving. A waveform is going to be produced by this ink. On the tip of this ballpoint we have ink, right? So that's how this waveform is going to be produced. Now we have taken a heart inside this diagram, human body diagram. Okay, and we have connected this human body right hand to the galvanometer with the help of negative electrode, and we have connected the positive electrode of this galvanometer with the left foot. Okay, now let's start. How does the action potential produces? How does it will put current into this galvanometer, upward deflection and downward deflection, and it will produce the ECG waveform. It will produce from the SA node. See, the current is going to be produced from the SA node. It is going to spread over these all atrial cardiomyocytes. It is going to produce this big vector. This is a wave of depolarization, so positive wave. See, positive wave. It is going away from the negative electrode and it is going towards the positive electrode. See, so atrial depolarization is going to cause, see, positive into positive is equal to positive deflection. So the needle will deflect to the positive side. Positive mean upward here. And this paper is rolling, so it is going to produce the P wave. See, okay. Now after that, the current is coming to this AV node. And we know that in the AV node, the current is so slow that the galvanometer doesn't detect anything, so there will be no deflection upward or downward. So this is the place when there is no deflection. The needle is like this, paper is rolling, but it doesn't deflect upward or downward. Well, so after that, AV node from the current from the AV node will go to the interventricular septum. Okay, and interventricular septum, when get depolarized, the current enter like this and goes like this in the interventricular septum. This is a way of depolarization, and look at here, it is going away from this positive electrode and towards this negative electrode. So this is a way of depolarization, which is a positive wave. Positive into negative equals to negative, and we know that it is a very small portion of the interventricular septum. Interventricular septum is a very small portion. Okay, so it is going to produce negative deflection. Okay, after that, what happens? The current will go down to the cardiomyocyte of the ventricle, which is the large ventricular portion. Okay, because current has arrived up to here. Okay, on these bundle branches. When we get the combined vector of the major part of the ventricles, it is going to be like this. This is the depolarization wave, which is positive, and it is going toward the positive. Positive into positive equals to positive. So the deflection will be positive. So when this paper is moving like this and it upward deflection occurs like this, because the ventricle is so big, see, so the deflection will also be so big. Okay, and then after that it will come down. Okay, up to here. Now the current, as we saw that it is going like this, see, on the bundle branches, and these bases are going to be depolarized at the end. And see, this is a wave of depolarization, right? Positive, and positive here is going, the arrow is directed toward the negative side, so it is going again to the negative side. Wave of depolarization, positive. Positive into negative equals to negative, and again this is a negative deflection, right, which is S wave. And see, again, this is a small portion of the ventricle, right? So it is going to produce this small wave, negative deflection. After that, what happens is that repolarization starts of the ventricle, and repolarization is opposite to the direction of the depolarization. And we also know that it should be a negative wave, or because it is repolarization, right? And negative is going toward negative, so negative into negative equals to positive. So this deflection will be positive. See, this is the needle, it will be deflected to the positive side. Now if the paper is rolling and the needle is deflected upward, so it is going to produce this T wave now. Okay, so P wave, depolarization of the atrium. Then this isoelectric line shows the current is passing through the SA node. This shows that the depolarization of the interventricular septum occurs, which is Q wave. R wave shows the depolarization of the ventricle, major ventricle, and this S wave shows the depolarization of the base of the heart. And then after that, isoelectric line, which shows that the heart has completely depolarized, and then repolarization starts. Repolarization of the ventricle produces T wave. Here we want to discuss something about the repolarization of the atrium. Most of the books says that QRS complex, when the depolarization of the ventricle occurs, at that time the repolarization of the atria occurs. But the atria repolarization wave is small, so it is consumed, or you can say the QRS complex can accommodate that wave inside itself. We have arrived at waves, segments, and intervals. Okay, so we already know that this is P wave, atrial depolarization. Q wave, this is interventricular septal depolarization. R wave, this is a ventricular, major ventricular depolarization. S wave, this is the base of the ventricular depolarization. T wave, this is ventricular repolarization. Okay, now we're going to talk about the segments. There is very simple thing you can remember about the segments is, whenever you guys see the isoelectric line, the straight line in the ECG, that will be a segment. So there are two segments, one is PR segment and other is ST segment. Okay, the PR segment is going to start from the end of the P wave and it is going to end at the start of the R wave. Why don't we say PQ wave, PQ segment? It's because most of the leads do not have this Q wave, so we will say PR wave, PR segment. Okay, and the next one is ST segment. It is going to start from the end of the S wave and it will be up to the start of the T wave. Okay, so this is known as ST segment. Now we come towards the intervals. These are three intervals which are important for learning ECG. Intervals here. Remember that interval is going to include at least one waveform, okay, or one waveform, one isoelectric line, or two waveforms. Okay, so it is a kind of mix. There are three intervals here. One is PR interval, and unlikely segment was starting from here, right? PR segment was starting from the end of the P wave and was ending over here. It is going to start from the start of the P wave and is going to end here. See? Okay, this is the first interval. Okay, the second one is QRS. See, it consists of three waveforms. QRS. This is QRS interval. And another one is RT interval. It is going to start from the R wave, see, R wave, and it is going to ends at the end of the T wave. It ends over here. I've made it a little bit longer, but don't mind it, okay? Now let's discuss about the graphical representation of the ECG. Normally, you are going to find two kinds of boxes in the ECG. One, large boxes, okay? This is a large box, okay? And inside that large box, you are going to find 5 small boxes vertically and horizontally, okay? Now let's see that horizontally we takes the time, okay, and vertically we measure the ECG with the help of millivolt, okay. And it all depends upon the rolling speed of the ECG under this needle, that how fast does it roll under this paper. If it is moving faster, this ECG wave will be forming with different speeds, okay. And if it is moving slowly, rolling slowly under this needle, the ECG waveform will be different. So the normal speed is 300 large boxes pass through this needle in 1 minute, okay. Now you want to see that how much time is needed for this large box to pass or roll under this needle, and then we will see that how much time is needed for this small box to roll under this needle. As we know that 300 big squares or big boxes are passed through this needle, under this needle, in 1 minute. 1 minute is equal to 60 seconds, right? You can divide this 60 seconds by 300, which will be equal to 0.20 seconds. This is the time taken by one big square to pass under this needle, okay. So 0.20 seconds. Now we know that every big square has 5 small squares. See, 1, 2, 3, 4, 5. So how much time is going to be needed to pass this small square under this needle, okay. So simply we can divide this one, see, this one by 5, okay, and we can find the time taken by one small square to pass under the needle. We can divide it over here, 0.2 divided by 5, 0.04 seconds. So this is the answer. It means 0.04 seconds are required for a small box to pass under the needle, okay. We can rewind it by saying that one big square is going to take this much time to pass under the needle, and one small square take 0.04 seconds to pass under the needle. So now we're gonna apply all these things on the ECG. Normal P wave is equal to actually 2.5 small boxes, okay, or you can say half of the big box, because big boxes consist of 1, 2, 3, 4, 5 horizontally, 5 small boxes, right? 2.5, and then okay, so 2.5 small boxes equal to 1 P wave, okay. Then after that isoelectric line starts, and that is also equal to 2.5 small boxes. Then the QRS complex, and see, the QRS complex is also equal to 2.5 small boxes. After that there is an isoelectric line that is known as ST segment, and it is also equal to 2.5 small boxes. But sorry for this drawing, because this line is too much longer. It's actually 2.5 small boxes. Okay, now see that we know that every big box is equal to 0.20 seconds, and every small box is equal to 0.04 seconds. Here 2.5 small boxes are equal to 1 p wave. Now if you want to find out the time, that how much time is taken by a p wave to be formed, is one small box is equal to 0.04 seconds, right? So 2 will be equal to 0.04 plus and half, right? Because p wave is equal to 2.5 small boxes plus 0.02. Okay, you can add it. 4, 4, 8, 9, 10. Put 0 over here. 1. Sorry. Okay, this is 1. So overall 1 p wave is equal to 0.1 second, okay, which is equal to 2.5 small boxes. Now let's see, 2.5 small boxes or 0.1 second. Okay, same is the case here. 2.5 small boxes, when you put 2.5 small boxes in time, one small box is equal to 0.04, so 2.5 will be equal to 0.1 second again. Same is the case with the QRS complex. 2.5 small boxes equals to 0.1 second, and so on. But forward, it's okay, it's not important, just need to remember these things. Okay, just remember one thing more, that PQRS complex then T wave, all of it is just occurs in one cardiac cycle, right? So if it is occurring in one cardiac cycle, this whole time will be equal to 0.8 seconds, because one cardiac cycle is made of 0.8 seconds, or you can say that one cardiac cycle takes 0.8 seconds to complete. Now we are jumping to the last topic of this first lecture of the ECG, which is Enthoven triangle. Okay, so Enthoven triangle looks really scary. Look at this. And it's scary because most of the students just trying to mug it up. Okay, but we're not gonna do anything like that. We're gonna explain everything very simply and clearly, and at the end of this topic you'll be able to see which lead you can use to find MI of which side of the which wall of the heart. Okay, so believe me and stick with me, and I need your full attention right now. Okay, so let's start it with this ugly diagram again. See, we have 12 leads in this ECG, right, that we are using in the normal daily routine in the hospitals. Okay, these 12 leads is consist of 4 limb leads, in which 3 are actually having voltage, but the other one, the fourth one, do not have. See, one to the right hand we connect, one to the left hand we connect, one to the left foot we connect, and one to the right foot. But remember, we're not going to talk about the right foot, because what happens is that the lead that is connected to the right foot is actually a neutral. Okay, so we can talk about 3 limb leads: right, left, and left foot, or you can say just foot, because whenever you're talking about the foot lead, you're talking about the left foot. Okay, so if I'm talking about the left foot or just foot lead, so or lower limb lead, it means that I'm talking about only left foot. Okay, so let's see that what kind of leads are over here. See, we will call it AVR, the lead which is connecting to the right hand. The lead which is connecting to the left hand should be called as AVL, and the lead connecting to the left foot is AVF. A mean augmented, V mean voltage, and F mean foot. Augmented voltage foot limb lead. Okay, augmented voltage left limb lead. Okay, augmented voltage right limb lead. Well, so now you see the heart is at the center. Just connect the heart to all these leads like this. See, like this and like this. So this is your AVL, AVR, AVF. Now connect the right limb lead with the left limb lead, and these are actually like this. Okay, this lead should be known as lead number 1. Now connect. Actually, the final thing that we are going to do is that connect all these lead and put it over here. Now we're going to connect this lead AVL with foot, that is AVF, and this is known as lead number 3, and we're going to connect this to the foot lead, and this is known as lead number 2. So if you see all together, limb leads are 6 in number. 3 of them are augmented voltage limb leads, that is AVR, AVL, AVF, and the vectors that we just drawn is 1, 2, and 3. AVR, AVL, AVF, 1, 2, 3. Okay, these are 6 limb leads. Now, when you're talking about the 12 leads ECG, still 6 leads are remaining, right? So the remaining 6 leads are actually put it on the chest. V1, V2, V3, V4, and V5. Okay, these are chest leads. Now let's bring this triangle out of this ugly diagram, and we're gonna put it in this way. See, 1, 2, 3, AVL, AVR, AVF. And that's not it. Actually, we're gonna put these all vectors in 4 quadrant plane, 1, 2, 3, 4. Still the heart will be in the center. What is the trick that you need to remember is that just put the tail of any arrow over here in the center and draw the vector in its own original fashion. See, we are going to draw one of the vectors. See, AVL. We're gonna put the tail of the AVL here. See, and draw it as it is in the above diagram. See, AVL. Same is the case with the AVF. Sorry, AVR and AVF. Okay, now look at this lead. Just put the tail of this lead over here and draw it as it is in the above diagram. Look at this lead number 2. Put the tail over here and draw it as it is present in the above diagram. This is lead number 2. This is lead number 3. This was AVF. Okay, now we need to put the chest leads, and don't worry, I'm just putting the chest leads and then I'm gonna explain why did I put it over here. Okay, what is remaining over here? Lead number 1. Lead number 1. Put the tail over here and draw it as it is in the above diagram. See, lead number 1. So 1, 2, 3, AVR, AVL, AVF. Okay, the chest leads we can put like this. See, 1, 2, V1, V2. Okay, and then after that V3, V3 over here. Sorry, V3 should be here. V3 and V4, V5, V6. Okay, got it. So all together 6 leads, 12 leads, 6 chest leads and 6 limb leads. Okay, now what we are going to do is to make you guys understand, I need to put it the 4 plane, 1, 2, 3, 4 quadrant plane in a human body. Okay, so this was the heart, it was in the middle. Why did I draw the AVF over here straight? I should draw it like this, right? Just to make you guys understand there is only one foot, right? So you can draw it over here or here, it's okay, the same thing, same concept. Okay, still I want to make you understand the chest leads. Okay, if you see the chest leads that we put on the chest, let's consider this is the chest of the patient. We put limb leads, AVR, AVL, AVF. Okay, and one to this side, but that is neutral. Okay, and then we put the chest leads, V1, V2, V3, V4. We go from this side to the lateral side, left lateral side of the body, like this. So V1, V2, V3, V4, V5, V6. See, we have put it in the same fashion. Okay, now let's see the it in the color code form so that you can remember it easily. This is on the chart. Okay, have a look, and if you want to memorize it, just pause the video and you can do it right away. Okay, now let me tell you that this is not a 3D structure. Okay, if you look at the 3D structure, actually this lead number V3 and V4, okay, these are looking at the heart like this, anterior side. See, this is the patient, this is the chest of the patient, this is the head of the patient, and these are the foot. Okay, and you are looking like this, V3 and V4 to the chest, anterior side. If I make this person stand, it will be like this, interior side. See, okay, V3 and V4, remember this thing. V1 and V2 are looking at the septum. See, interventricular septum. I have drawn this heart a little bit down, but I would have drawn it a little bit above. Is because of my drawing, but V1 and V2 are going to look at the interventricular septum and the atria. See, the atria. Okay, 2, 3 AVF, 2, 3 and AVF. These are the leads which looks under the heart. Okay, under the heart. Let's consider this is your heart. Okay, it is going to see under the heart to see, so it see the inferior wall. Okay, while V3 and V4 see the anterior wall. Okay, V1 and V2 see the septum and atria. The remaining is V5, V6, 1 and AVL. Look at this, look at the lateral side of the heart, so it is going to see the lateral wall of the heart. In order to summarize it, just look at this one. V1, V2 is for septum and for the atria. V3, V4 is for the anterior wall of the heart, and V3, 2, 3 and AVF is for the inferior wall, and V5, V6, 1 and AVL for the lateral wall. See, now what we do for the posterior wall. Sometimes we say that this V5 and V6 you can put it on the back side of your chest, or you can say on the back of your thorax, and you will be able to see the posterior side of the heart because see, the chest leads most probably see like this to the heart, okay, and the limb leads see like this to the heart. So let's consider, if this is the heart, you look like this, these are the chest leads, and if you look like this horizontally, these are the limb leads, okay. So now once we have done with basic concepts of ECG, in the next lecture we are going to start the proper ECG, and in the next lecture we're gonna cover the heart rate, okay, how to find it. There are 3 ways, and then after that we're gonna go to the normal axis of the heart and axis deviation of the heart.